Okay, so yeah, we've got the same number for dogs now. So what I can now do, and I wish I'd drawn this on the smartboard, I can now slide the two ratios together so it looks like this. So I've slid the two ratios together. I could only do that once I've got the D number the same in both ratios, which just meant in this case multiplying that one by 5. So I flipped everything around so the common number was in the middle, the common letter, sorry, was in the middle, and then I wrote it. Now then, the question says, what's the ratio of cats to fish? So, which is a bit of a nasty trick, isn't it? Because if you just take the dog number out, you've got a ratio that you can simplify. I couldn't simplify it when the dog number was in there, so the final answer to that one is 1 to 10. Any questions? Okay, right, let's do the second. Let's do the second one then. So if I've got a ratio of red sweets to ones that aren't red, so basically the reds and all the others of 2 to 3. Callum, what fraction of red?
2/5.
2/5. It's really important that you can see that, not 2/3. Okay, a ratio of 2 to 3 means the reds are 2 shares and everything else is 3 shares, 5 shares altogether. So that means that red is 2/5. We've got a similar story with green. So Ollie, what fraction are green if the ones that are green 6 parts, not green 19 parts? Not such a nice fraction this time.
6/25.
6/25, brilliant, yeah. And so the rest are blue. So this is a fraction addition sum really, because if I can add those two together, whatever's left will be the blue sweets. Now of course, Bradley, if this was on a non-calculator paper and I wanted to add these two fractions together, what would I have to do to enable me to do that?
You times the red sweets by 5.
So I'd change that one into 10/25 by just multiplying top and bottom by 5. So I've got 10/25 are red, 6/25 are green, so the rest must be blue. So Kai, how many 25ths will that be? 9 25ths, brilliant. Now the question says what's the ratio of red to blue to green? So red to blue to green. Well, if it's 10/25 to 6/25 to 9/25, I could write that as a ratio. I've got to get the numbers right, so it's red, blue, green, got that order right, so it's 10, 9, 6. So 10 to 9 to 6. Now, how did I know that that was a fraction question, whereas this one I didn't use fractions? Well, I wouldn't mind betting that you could have done this in a similar way to this one, but I think fractions were a little bit easier. And don't forget, you've got all these different techniques with ratio. Changing it into a fraction is one of those. So if you're stuck, does that help in any problem? Did anyone get anywhere with this one? Didn't really give you much time, did I? Right, I'm going to draw a picture for this one. This is a tricky question. There's no two ways about it. I'm going to draw a picture of the ratio of A and B. Okay? I don't know what it is we're sharing, what A and B are, but let's just say that it's Alfie and Bertie, and they're sharing some sweets in the ratio 5 to 1. Okay? So here's Alfie's sweets, he's getting 5 shares. And here's Bertie's sweet, he's just getting 1 share. Bertie's been a naughty boy. I don't know how many sweets they're sharing, so I'm just going to put an X. That's what I tend to do in maths when I've got a value I don't know. I'm just going to put an X. So the total number of sweets they shared is 6x. 6x. wipe the board and then don't dry it. Okay. So Alfie and Bertie have shared some sweets. We don't know what it is, so we'll call it 6x. Camilla and Deirdre are sharing some sweets. I think we're with Deirdre. Yeah, I was about to say my mum's called Deirdre. Yeah, my mum isn't called Deirdre. Neither is your mum, Max. But there you go. I don't know how many sweets they're sharing, so I'll call them Y. I've used X, so I'll call them Y. So they're sharing a total of 5 Y sweets. Now comes the key part of the question. We're told this, and what that means is the number of sweets that Alfie and Bertie are sharing is double the number that Camilla and Deirdre are sharing. So it means that these sweets, that we didn't know how many it was, so we called each box X, so 6X, is equal to 2 times 5Y. Now what I can do now is I can now get an equation for X in terms of Y. I could say that X is equal to 10Y divided by 6. Or I could get an equation for Y in terms of X. Y is equal to 6X divided by 10. Now 6X divided by 10 is 0.6. 0.6X. 10Y divided by 6 is a horrible recurring decimal. So I'm not going to do it that way. I'm going to do it this way. So what that means is that each of these boxes is actually 0.6x. So what's the ratio of A to B to C to D? Well, I know that Alfie got 5x of sweets. We don't know what x is. We don't need to. Bertie, short for Bertrand, got 1x. Camilla got 2y, which is actually 1.2x. And Deirdre got 1.8x. Now there's a couple of things wrong with those ratios. They've got letters in them. So I can get rid of the letters, just divide them all by x. Because you can do that with ratio, can't you? You can divide, as long as you divide everything by the same thing. That's the first thing wrong with those ratios. The second thing wrong with those ratios is I've got some decimals. So what would be a good way to get rid of those decimals? Jack, what could I do to those numbers to get rid of those decimals? What can I do to 1.2 to... Remember, I can, with a ratio like a fraction, I can multiply, as long as I multiply everything by the same thing.
Oh, multiply it by 5?
Could do 5, but would we agree it's probably easier to do 10? Because I can easily multiply by 10. So I've run out of space, I'll have to rub out my original picture. This will be on my YouTube channel though, so if you want to look back at this. It's,
How do you get 0.6?
Right, hang on a minute, let me finish multiplying by 10. Were you happy that the sweets over here added up to 6x sweets? Because there were 6 boxes, 5.
Yeah.
And the sweets over here added up to 5y. And we're told that the number of sweets that A and B shared was double the number that they shared. So I said 5x is equal to 2 lots. Sorry, 6x is equal to 2 lots of 5y. And I worked out from that each y was worth 0.6x.
Oh, you divide by 10?
That's right,
Right,
yeah.
yeah.
Right, I'm nearly there with this one. I can simplify that ratio because they're all in the 2 times table. So that's my final answer. (25 to 5 to 6 to 9). And if you found that hard, well, don't worry, Mrs. Mogster and I had to sit down and scratch our heads and spend some time over that one. So yes, it's you're in good company. You're in good company. Yeah, I'm going to rub out the rest of the picture, but there we go. Right, so I'll stop recording because So this journey here, 2, 6, any journey which is a multiple of that journey, so for example, 2a, which would be 4, 12, or 3a, which would be 6, 18, or minus 4a, which would be minus 8, minus 24, or a half a, which would be 1, 3. These are all parallel. They are all parallel. So any multiple of a vector will give you a parallel vector. Multiplying a vector, and we say multiplying a vector by a scalar, because if you remember from science, the opposite of vectors are scalars, which are number quantities that just have a value, but just say multiplying a vector gives a parallel vector. And we can say more than that. So we can say that, for example, I multiplied by 2, so this will be twice as long. I multiplied by 3, so this is 3 times as long. I multiplied by minus 4, so it's 4 times as long. But what else will have happened? It's going in the opposite direction. Yeah. So it's still parallel. It's just one vector's going along to up 6, and the other vector's going down that way. Still parallel. Still parallel. So identifying parallel vectors is one of those things that often crops up in questions. If you've got any vector and you multiply it by any number, even by a fraction or a decimal, you get a parallel vector, a vector that is going in the same direction, albeit shorter or sometimes in reverse. Parallel vectors. Right, so finally, plenty of time, which is good. I want to talk about using vectors in geometrical problems. So we're going to have a little objective at this point, which is vectors and geometry. And what I'd like you to do is I'd like you to draw me just a little old parallelogram. Okay, just a little parallelogram. Okay, and I'm going to call my parallelogram A, B, C, D. There we go. So that's a parallelogram. I've drawn a parallelogram. Here, if anyone wants. Now, I am going to tell you about 2 vectors, 2 journeys. One vector is the vector little a, and little a is a journey which just so happens to be the same as the journey from A to B. That's little a. But remember, whilst the vector AB with an arrow over the top is fixed, it goes from there to there, little a could be anywhere. It's just any journey that's that length. I'm not going to tell you the numbers for little a. I'm just going to say that's little a. Let me tell you about the second vector. It's called little b. And little b just so happens to be the same as the journey from A to D. But it's not fixed. It could be anywhere. So my first question is, can you label anywhere else on your diagram a vector which is the same as A and the same as B? So Sean, I videoed the end of the ratio starter, and I've just started videoing the key bit of this lesson where we've just talked about parallel vectors, and we're now getting into some geometry problems. So can I get you to label anywhere else on your diagram where you can see a journey that's the same as A, and anywhere else on your diagram that's a journey the same as B? I'm hoping that you spotted that because this is a parallelogram, that's A and that's B. They're the same journeys. Remember, vectors, unless they use the capital letter descriptions, vectors are not fixed in space. Note also there's no column vector. I'm not telling you what A and B are. We're just dealing with them now like algebra. So now I've got my whole parallelogram described in vectors. You can describe some journeys for me. So for example, the journey from A to C, I can go two ways, can't I? I can either go along here and along here, or along here and along here. Whichever way I do that, I end up with an A and a B. One way is B plus A, one way is A plus B, but it's the same thing, isn't it? So can I get you to describe some other journeys for me? Hello, Anna. Anna, I videoed the end of the ratio starter, so you can see that, and I'm videoing a little bit of this lesson as well. So. No, I'm not going to do that.
That's actually the name of the math.
So, Arthur, how can I get from B to D, travelling using my journeys that I know, little a and little b?
You would do B minus A.
B minus a, yeah. Or minus a plus b. Are we happy that's the same thing? So to get from B to D, I can either go this way, which is along B, and then backwards along A, which is the way Arthur suggested. Or I can do backwards along A and along B, minus A plus B, which is the same thing. So I'm just going to leave it the way Arthur suggested. That looks pretty good to me. So to get from B to D, along B, and then backwards along A, which is minus A. So Katrina, how can I get from D to B?
B minus A? No, I don't know.
Well, which way do you want to go? Do you want to go up or do you want to go backwards?
Backwards. Oh, minus A.
You're going to go that way, okay. A,
Minus
A minus B. And can you see how these two journeys are related? This is a B and a minus A, and this is an A and a minus B. They're related, aren't they? Now, what about this point here? This point is halfway along the diagonal A to C. Yes?
What if you do the arrows the other way around? Would it make any difference?
Well, absolutely, yes. Yes. So, for example, what I've got here is the reverse journey, isn't it?
Yeah.
So from B to D, you're doing B minus A. So if that arrow was the other way around, it would be minus B.
How do you know that you have to do it that way?
That the diagrams are always given.
Okay.
Okay, so you always start with the diagram. Yes, Arthur?
To get to the midpoint, would you just have half B plus half A?
Yeah, yeah. A to C is this. So A to M, well, you've got to think, okay, A to C, I'm doing it this way, but the effective journey is there, isn't it? A to M is halfway along there. So it's going to be half of this journey here. It's going to be a half of A plus a half of B. Now, this is where vectors gets a little bit weird because, you know, we're no longer telling you that A is 6,2 and B is minus 8,3. So I can't actually put numbers in. We're almost sort of, you know, we're leaving it in terms of algebra. And you might say, well, hang on a minute, I can't get to M because it's not on any of the journeys. But can you imagine? It's a bit like going off-road. To get to M, you go along here and along here, don't you? That's how you get to M. That's halfway along A and that's halfway along B. But you don't need to worry about that because with vector problems you can say, okay, A to M is halfway along the journey A to C, and I've defined the journey A to C, so it's just half of that. How much time? Plenty of time. Could you draw me now a triangle? I'll zoom out a bit so that's clear. I will show you. Oh, hang on, I've gone funny colour. What's going on there?
There it is.
Thanks, Thomas.
Let's go.
Okay, so this time, yes.
So that line in the middle is shorter than variable length. Round,
Yes, so this is where you've got to we're saying this journey here, it's not a different journey to this. It's the same net journey, isn't it?
but would they be shorter?
You're absolutely right, but think about where you end up in relation to where you started. You end up the same distance and the same angle away from where you started. So vectors, it's not so much about the total distance, it's about where you are relative to where you started. It's, like I said, weird, but perhaps not very hard. Not all the time anyway. Okay, so I've got here a triangle, and I'm only going to tell you about two journeys. Okay, I'll call the corners X, Y, and Z. So, my question is this. In this diagram, how can I get from Y to Z? There's no journey. Or is there a way of doing it? So, Harry, is there a way, Katrina, this way is where the action is, all right? Harry, how can I get from Y to Z using roads that I know about? Genius. Are we happy with what Harry just said? I can't get from Y to Z this way because I don't know what that vector is, but I can do minus A plus B. Now I know what Kai is saying is absolutely true, that that's a very different journey to that, but when we're dealing with vectors, it's just about where you end up relative to where you started. So actually, that journey is the same as this journey. The overall effect is you end up here. So the journey from Y to Z can be described like that. I can't use this road because it's not described with a vector. Okay, here's a point, and I'm telling you now that the distance from Y to D is in the and the distance from D to Z are in the ratio 1 to 2. Okay, so the distance to here and the distance to there are in the ratio 1 to 2. So I guess the first question is, what fraction of the way down there is that? So what do you reckon, Max? If that's in the ratio 1 to 2, how far down the line is that? What fraction? 1/3. Brilliant, brilliant. Are we happy with that? So Y to D is 1/3 of Y to Z because we're told about that ratio. So, and this is, it's a bit weird because there's no numbers involved here. So we say, right, YD is 1/3 of that journey that Harry told us about, which I can multiply out just like and can you imagine going off-road? That's what we're saying we're going to do, isn't it? We're going to go off-road. To get from Y to D, we're going to go minus 1/3 of the way down there, and then 1/3 of the way along there. That's minus 1/3 of A, and that's 1/3 of, oh, wrong way. And these are the sort of weird but not hard geometry problems that we're going to spend a lesson or so looking at. Well, certainly tomorrow. Oh, I see you twice, don't I? You don't see you on Friday, so 2 more lessons this week. Okay, we will leave it there. Good stuff.